So my name is Trevor Jones. I am the EV team lead for suspension, I should say. Suspension team lead for EV is here. So this is the presentation for the suspension on the EV car. So first things first, I want to go through and just make a couple of acknowledgements. Suspension's extremely complicated. I don't know everything. I know, in fact, extremely little. I'd argue some of the recruits probably know more than me by now, which is great. So don't expect to master everything here. There's a million great references to go off on the SVN. There's a lot of complexity to a lot of them. There's a lot of things that are going on here, a lot of variables to work with. You can't just assume that reading through one textbook and designing something you're an expert. Some of the guys in the industry that have been working 40 years, they might know a thing or two. We definitely don't. So go into suspension with that expectation that there's a lot going on there. You have a lot to learn, but there's a lot there you can enjoy about it. And obviously there's more to what's given here. This is just kind of an introductory attempt to kind of get an idea of what suspension is, what the EV suspension for this vehicle is, and kind of why I designed it and how it's designed. So in general, what is suspension supposed to do? The biggest thing is control tire loads. That's where a race car design starts. You have to start with the tires, find your tire loads, and you work up to the driver from there. So all the forces is generated with tires. It dictates directly how the vehicle can perform. So the suspension and controlling those forces is extremely important in this. It's very common to say that suspension is the first thing you have to design when you're designing a race car. A well-designed suspension system, so it makes the vehicle predictable. It allows the vehicle to behave as the driver expects. That includes things such as oversteer and understeer, and allowing the driver to go into corners confident that he knows how the vehicle is going to perform, how it's going to do on straightaways, how it's going to do on its braking, all of the handling characteristics suspension's a part of and really kind of controlling. So on the background research, we have a lot of references on the SVN. The Millikan and Millikan text is a very good one. It's extremely complex. They kind of just dive right into it. It can be really hard to read, really hard to follow. There's a lot of really good intermediate documents though. Learn to Compete, Vehicle Load Transfer. There's a design case study on that that's really good. How to make your car handles good. There's a text on Bellcrank optimization, which I'll get into later. Those are great to start and get yourself interested or kind of begin with on what suspension is supposed to do in the simple terms, get some good ideas for how the nomenclature works and what are the different terms and kind of some of the main things you have to go with. So what are the main requirements, at least based on the rules? Based on the rules, you have to have 1 inch travel in both compression and jounce. It's what's technically referred to. I've always known it as rebound. In the mountain bike world, that's what it's referred to. So I've always just gone off of rebound. That's basically, you have to have 1 inch both ways, so you have to have a total of 2 inches travel. Other rules tend to be for the fasteners and safety concerns, such as safety wiring and whatnot, which means the suspension engineer for this has a huge amount of freedom that they can enjoy to go through on what design they want to go with. With that in mind, there are quite a few systems that have already been designed that have been kind of proven to work pretty well. So you want to kind of keep that in mind, but there are some designs you can still come up with that I'm sure have been tried and tested and not done so well that you can definitely give a shot. There's no reason to think that you can't design something because it hasn't been done, and there's also no reason to think that a really good design that's been proven before can't be done again. They're just copying someone. So yeah, again, freedom on this is awesome. So it's a really good creative sub-team to work on if that's kind of what you're looking for in the mechanical sense. So some guidelines for suspension. So these are kind of the main things you want to be looking at. So compliance or play is really the enemy of suspension here. You don't want to have any compliance through the system because that's taking away the effects of the shocks, which is what's actually absorbing the force, turning that into heat basically. If you have any suspension, any flex, you're introducing additional forces, additional moments, you're putting unnecessary strain on your system. Most of the suspension components can run relatively low factors of safety, like in the range of 1.5 to 2. As soon as you get extra compliance in there, you're really pushing your design. So you want to try to reduce all friction in play, and that makes sense. You want it to be super rigid. Rigid in the fact that everything between the tire and the shock is nice and sturdy. You're not going to lose any of your energy there. Everything into the shock is what's going to be lost. That's all your energy transfer there. So also you want to understand the difference between sprung and unsprung weight. Sprung weight is pretty much everything from the shock inside of the vehicle. Unsprung weight is the shock to the outside, meaning the tires, the uprights, the brakes, and your accompanying components for that. When you have a lot of, you want to minimize your unsprung weight as best as you can. The reason you want to do that is you have a very small unsprung weight. It means you have a very large amount of sprung weight, which means there's a huge amount of inertia in the chassis that doesn't want to let the tires move, meaning you get amazing traction. That's the simple thing. Go for it.
Yeah, so you had mentioned, you kind of brought up like factor of safety on some of the suspension components. Would it be better to look more at the deflection of your part than necessarily just the factor of safety? Because
Yes.
if you have a factor of safety of 1.5 and you know it's not going to break, it
Right.
might be deflecting more. So.
Right, exactly. So you do want to pay attention to that, especially in terms of bell cranks, and I'll get into that versus a one-piece bell crank versus a two-piece bell crank. We will get to that. As a general rule of thumb, factor safety is a good place to start. Deflection is another great place to keep looking at. That's a very good point. Thank you. So yeah, just again, when it comes to lower unsprung weight, that's always more advantageous, which has kind of made the EV car design kind of wacky because we've got the hub motors, which immediately is throwing a significant amount of weight on that unsprung side that the suspension now has to handle. So it makes it kind of fun. And so for the continued EV vehicles, that's something to keep in mind. Question?
Just to clarify, so your sprung weight is the weight that's, it's the force that's going into the shock.
So your sprung weight is on what I'm going to call the inside of the shock. So if you have, let me say it like this. If you've got your shock at this point and all of your suspension components and your tires out here, so if you're looking for your vehicles all on the right, or excuse me, your tires all on the right and the rest of your chassis vehicles on the left. Your unsprung weight is all of the components that transmit from the shock out to the force in the road, right? That's what the shock has to directly control, those forces and those weights. Your sprung weight is what's being suspended by the shocks and the suspension, and that's why it's referred to as the sprung weight, because there's a spring holding it. Okay, that's kind of where the name comes from.
Yeah.
That is your chassis, your driver, all of your components held within the chassis and the body and whatnot. Does that make sense?
Yeah.
Okay, is everyone clear on that? Go for it.
So the more unsprung weight you have, is it the less weight the shock's able to absorb and the less?
So if you have lower unsprung weight, that means there's less forces and moments being created for the shock to control. Your shocks are going to have to control something, obviously. You can't have no unsprung weight. That wouldn't make any sense. But the more you dump onto that tire side, the larger forces your shocks are going to feel. So if you had a minimal unsprung weight on both sides and you dive hard into a corner, your shocks are going to take some of the force, do pretty well. If you have a huge amount of unsprung weight and you dive into a corner, you've got a significant amount of force going right into the shocks that the frame and the chassis now has to help make work, basically. And as soon as you have so much weight that the frame has to go against, you're starting to lose traction at the tires. And again, the biggest thing on suspension is you want to be working with tires and you want to make sure that you're keeping traction, you're keeping your slip angles and whatnot. We'll get into more of that. Go for it.
It also puts a lot of a higher moment of inertia on the suspension that's moving up and down, right? So your tires want to move up and down to account for the ground, the unevenness of the ground. And if you add more weight out there on the stuff that's moving up and down, it makes it not want to move up and down as much. Which makes the tires not stick to the road as well, which means less grip.
Yeah, so another way to look at this is, again, if you take a force on a shock, bounces the tire up, it has to reset. That's a significant amount of force. You have a longer time it takes to reset that amount of force, and it takes a longer time to get your traction back. Is that everyone clear on that? I know this is super complex. Go ahead.
Yeah, so basically, are you saying that you have to try to get all the variables into the sprung weight?
Yes, you want to try to keep. Yeah, you want to try to keep everything on your sprung side. Weight-wise, again, you don't want to obviously minimize weight to the just like, as low as you can go, because you're going to have issues with that as well.
Yeah.
If you're trying to do weight saving, suspension may not be the best place to start. Body, maybe chassis, you don't want to mess with chassis too much, but definitely like things like body and maybe motor controllers, batteries, where you can shave weight here and there. Suspension, you want to make sure it's going to work and it's going to be solid. So you want to keep all your variables in mind of how can I minimize all of my weight here. And of course, there are certain designs like what we have now where we're just going to have significant weight in those wheel hubs and we just have to deal with it. That's the way the vehicle's designed. Now it's our job as suspension to make it work. So that's just kind of sometimes the nature of the beast. You just have to go for it. But you do want to keep in mind that difference between them. From what I've read, you want to keep motion or sprung to unsprung weight ratios at about a 5-to-1. So you've got somewhere around 20% of the weight in the wheel, 80% on the chassis. Spread across all four.
Yeah, that's what I was going to ask. Like, is there going to be some sort of ideal ratio?
Yes. Yes, you want to pay attention to that. Some of the texts go pretty in depth and mention your components that connect between the two. So like your control arms and your push rod connects between the unsprung and the sprung, right? Well, that you have to distribute about 50% of each to the sprung and the unsprung calculations, whereas your upright's strictly unsprung, your chassis is strictly sprung. So it can get pretty complex into it, but a main rule of thumb, a good 5 to 1, good baseline. 2 to 1, not nearly as good.
Now, is there any particular, like what, I mean, just from a high level perspective, like, is there a specific reason that 5 to 1 is the ideal ratio and not like, say, 6 or 7? And just totally minimize the unsprung?
The text that I've read said 5 to 1 was good. I didn't read any further into why you'd want to go more than that, less than that. It just said that was a good baseline to start with.
Okay.
And from what I understand, like as a big picture, this suspension is a bridge between your sprung forces and your unsprung forces. Right?
Yeah. Yeah, again, because all of your forces, they have to be controlled somehow. Where does the force go? Through the tires, through the uprights, through the control arm, shouldn't be through the control arms, through the push rods into the shocks where they're converted to heat. That's where your energy stops. It should stop there. Of course, you're going to get some vibrations, and if you were diving through your suspension and slamming into the end of it, you're going to get a couple extra forces there. But suspension needs to control everything there and dissipate it all to heat.
So if it's the bridge, then you need to change your position, like your placing of your suspension, such that the forces from where you want your unsprung weight to be, or sorry, your sprung weight to be.
Your sprung weight, yes.
Such that the suspension is in between the two, right?
Yeah, you want to try to keep your suspension as that bridge directly between the two. And we'll see as I get into this that I didn't do the best job of that. We'll get into why I kind of had to do that, and we'll go from there. Any other questions on sprung, unsprung? Because it's a very key topic for suspension that I want to make sure everyone's kind of understanding. All good? Okay, cool. So we'll go to the next thing. So some common components of suspension. The upright, so that's what's shown there in blue. We're machining our own this year, so quite a bit of weight in those, quite a bit of complexity, pretty fun stuff. You have your control arms, so that's your A-shaped top and bottom members. Your tie rod, which is that black horizontal member right here. The bell cranks are the yellow, and that's working off of a vertical, or I shouldn't say vertical, but this design here is making the shocks in line with the vehicle, which is a lot of the way I think the formula does them. Pretty neat. The shocks, the dampers, I'll be using those words interchangeably. If there's any confusion on those, please ask. But a shock and damper, they do the same thing. That's the red, and then the anti-roll bar, which I'll get into further. That's kind of hard to see. It's this white bar right up here that dives into the body. And I'll get into what that is and why it's important and why it's nice to have. So how these components themselves work. So up here we've got some of the common ways that you can control what's referred to a degree of freedom. A degree of freedom is a direction that it's allowed to move. So if you take your tire, it's got 6 degrees of freedom. It can translate in all 3, and it can rotate about all 3 axes. We got to control all of those in one way or another. So simple tension compression links, like a push rod and a tie rod, those only transmit forces in and out, so you only got 1 degree of freedom. Your control arms, like your A arms, allow you to do 2 degrees of freedom. So does your McPherson strut, and that uses kind of the damper built into this strut already, kind of like this is here, so that your spring's built onto that strut. That also controls 2 degrees of freedom. So with this, you want to make sure you're controlling, again, all 6. On the front suspension, you are locking 4. You're leaving your steering open, and you're leaving your vertical motion open. On the rear, you have to lock 5 because there's no steering in the rear. You just need vertical motion. Does that make sense to everybody? Cool. So yeah, there's the compression again. So the disadvantages and advantages, I didn't explain, but the picture on the left side was leaf springs. Everyone's seen a leaf spring before, know what it is, like on the old trucks and Jeeps and stuff. So a leaf spring, they're great for high tire loads, but they have absolutely no tunability. They're very simple, but they take up a lot of room, probably not the best design for FSAE vehicle. Your McPherson struts, they're simple and cheap as well, but they're located so close to the tire that it can be really hard to jump that distance between the tire and the chassis. As we notice, most of the FSAE cars, the wheels are so far away from the chassis, you really got to jump it one way or another. That's why most teams go with the 2 A-shaped control arms, one upper, one lower, a tie rod or steering rod, and a push or pull rod. Push or pull rod do the same thing, just in different directions. I'll get into that a little bit later. And again, it's a simple, very reliable system, offers a pretty significant amount of tuning, and still pretty easy to manufacture with what we can do here, which is convenient for us. So the bell cranks, this is a very key point. This is where a lot of your motion is going to be coming in on the suspension. These transmit the forces from the upright into the shock through a pull rod, or push rod, I should say. And so that there's a motion ratio that connects the wheel shock to the wheel travel. And that's a very key thing in these because that's where you're going to get your wheel travel to shock travel. So as your wheel is traveling 2 inches up, and you've got 2 inches into your shock, you're running a 1-to-1 Bellcrank ratio. If you're running a 2-to-1, then you're getting 4 inches of travel at the wheel for 2 inches at the shock. The reason this is important is the rule stated we needed 2 inches of travel. So it's very convenient to use mountain bike shocks because a lot of them come with a 2-inch stroke, what it's referred to. For those that don't know, stroke is this distance here. It's the distance that the shock can telescope into itself. It's how much travel the shock actually has. So by having a 1-to-1, or I should say close to 1-to-1, gets us right there on the rules. For a little bit of a factor of safety on this, I believe mine is like a 1 1/8 to 1. So I've got just a little bit more tire travel to shock travel, just in case we do have any compliances in the suspension, some of the welds are a little off, there's any issues in the frame, small things here and there. That way, if I did an exact 1-to-1 and we only had 1.95 inches, we'd be disqualified. So I'm engineering just a little bit extra into that just to be safe. And so yeah, that's why we use the mountain bikes, because the mountain bike shocks, they're just super common, they're super easy to work with for the most part. Go ahead.
2 questions.
Yeah.
One is the push rod a Bellcrank?
No, the push rod is not the Bellcrank. So if I can attempt to go back to where's that one slide here. So the yellow here is the Bellcrank, whereas this is the push rod here. And so what it's doing is as you get a force coming off of the upright and the tire, it's going to be pushing this into the Bellcrank. The Bellcrank is going to rotate and compress the shock.
Okay, so my second question is, just I'm kind of thinking about it. The way that you guys are able to get the 1-to-1 is obviously you have the force that's going completely vertical. You take a certain component of that going into the push rod, and then the reason why, like the way you're able to get it is you make the radius where the push rod hits the Bellcrank smaller than the radius that's actually connected to the shocks.
I didn't go quite that analytical into it, but yeah, you're on the right
Like if
track.
you have a small rotation and at the bottom part it's going to make a longer rotation and have like a...
Yeah, so that's if you're going for like a progressive design. Go ahead, Cameron, you're mentioning something?
You got it backwards.
Is it backwards?
Longer on the side where the Bellcrank or where the push rod comes in because you want the wheels to travel further than the shock.
Right, it'll make a smaller motion into it. Okay.
Yeah. Right. Go ahead.
So our suspension system isn't going along sort of a progressive design, but more like this.
It's a straight up just 2 inches here goes to 2 inches here. The progressivity will come in with the shock, and I'll get into that a little bit later as to why we chose the DVO shocks and why they're so nice to use. But yes, so the way I ended up designing this, and I'll go into it, is I just did iterative. I didn't have the time to go through and develop the analytics of what we had. I just pretty much said, okay, I'll start with a rough triangle about this shape. If this is my midpoint at resting, here's my max, I need to be completely compressed. Here's my most open, I need to be completely extended. And then I was like, okay, that was kind of close, and then just iterating the Bellcrank geometry ever so slightly so that I would come to a point that gave me about a 1 1/8 to 1 Bellcrank ratio.
And then, according to the rules, the 1-inch compression, and is that any given shock can only move up to 1 inch? Or
No, that is the wheel travel itself. That's where it is. So all the rules say is it's got to be 1-inch compression and 1-inch rebound off of that, so 2-inch total. And so if you have a shock that has a 1/2-inch stroke, you just develop a 4-to-1 Bellcrank ratio, motion ratio, and you're good to go. That way you get your 2-inch travel out of only 1/2-inch gear. I don't know why you want to do that, but you can. That's the idea. If you wanted to go with an 8-inch shock, and you could. That way you can go for like a 1/4 to 1. So you get like huge shock displacement for small tire displacement. What else?
If you're dealing with like a higher ratio, like 4-to-1 or something like that, does that mean that the shocks or the dampers that you're using, like that one that we have over there, does that mean that there's not a lot of variation? Because obviously, like it depends on the velocity that you're.
Right, exactly. That's something to keep in mind. If you have a very short stroke, that's not a lot of distance and force you can generate, or you're going to generate a significant amount of force in a very short time. That might not be the best way to control your suspension. If you go to a really long shock, you can generate a lot of force over that long time, but it might take so much time and be so long and not really fitting the design of the car. Because obviously we have size restrictions. We can only make this so big. There's no reason to make shocks that are 8 inches long and make it work. Because they sell those for mountain bikes that are huge. Now granted, that's 8-inch eyelet to eyelet. I think those run like 3.5-inch stroke. So it's things to keep in mind. So that all makes sense for Bellcranks? So next, shocks. So again, I mentioned before, mountain bike shocks are common. They have a very common 51mm or 2-inch stroke rate or stroke distance. That's why we use them, since again the 2-inch travel that's required, it's super convenient. Just bam, 1-to-1, slightly over engineered, you're set. And again, these are dampers. So this is where I'm going to deviate a little bit from the shock versus damper nomenclature. A damper creates force proportional to velocity. A spring creates force proportional to the distance it's displaced, right? So there's a subtle difference there that I want to make sure everyone's aware of. So the way, I'll get into the DVO shocks and how we're going to use those, but that's something to keep in mind. That's how the dampers work, and so it's all based on velocity. And so how we do that is based on low speed, high speed, and there's also intermediate speed. A low speed impact is anywhere from 0 to 2 inches per second or 0 to 51 millimeters per second. And so those are your small, soft, rolling bumps, like going over a speed bump really slow. That's your low speed. Then there's high speed, which is 8+ inches per second or 203 millimeters or more per second. That's something like hitting at speed, you're going 70 miles an hour on the freeway and you hit a pothole. That's a very fast impact. That's referred to your high speed. There's an intermediate speed between these. We don't need to worry about them too much. All of our tuning tends to happen with the low speed and the high speed. So there's two common types of these, the coilover and the air. I'm going to use DVO for both of these just because I happen to like the company and it's easy to explain what's going on with them. So these are the coilover shocks. This is the DVO Jade. It does the exact same thing that the Topaz we have here does, just with a different configuration. These tend to be a little more simple. They work just like a coilover shock and pretty much anything else does. You've got a main coil that's on a, just being held between two different plates, and then within it you've got a damper, and that's what all of this is here, from all the way to the tube, all the way up to this is your damper. That's what creates your dampening of this. So it's a combined spring damper system. These offer very supple small bumps, so they're really, really sensitive to the really small stuff. And mountain biking, that's awesome. For our for what we're going to be doing, since we're on road, it's not going to be quite as bumpy as we'd see on a mountain bike on a dirt road or something like that. Not quite as important, but still interesting to know. The big adjustment here is the high and low speed compression adjustments. And so again, compression is the shock being pushed together. So you have a low speed adjustment, so you can fine tune how soft it is or how stiff it is at the low speed. And you have a high speed for the really big impacts. So like if you're jumping on a mountain bike. Obviously, the biggest we'll see is when we're throwing the car into the sharpest turn. So that has an adjustment there to kind of tune them. We can also adjust spring preload. So this here is working off of a thread where we can crank it down to make it tighter or to make it looser if we want to. That is basically how much sag we would be running. Sag is just like at resting weight, how much displacement are you taking up. Then there's also rebound adjustments, so how quickly it's going to bounce out. We can adjust how slow or fast that is. The problem with these ones here is the spring rate is linear, and we can only shift that linearity by the material of the shock we use. Steel and titanium are the most common, and they usually come in different weights, usually like 550 pounds per inch, 650 pounds per inch, 450 depending on the rider. So they can be kind of difficult to tune with, especially if you've never worked with one before. You just kind of throw on a 550 pound spring and take some data and hope it kind of works out, and sometimes it does, sometimes it doesn't. So where we like to go with this is the air shocks, and the air shocks are awesome for a lot of reasons. So that's what we're using here. This is one of them. We've got these same things on the IC car downstairs in the shop, which is pretty sweet. So we can actually get test data from that, which will be pertinent to this vehicle, which is really, really cool. So these ones here, they also work like a spring damper system, but it's all through air. So the way these work is a force is transmitted into this. This shaft here goes into your, it was kind of thrust upon me. I'm getting it done. It's going to work, hopefully, and we'll kind of take it from there. But it's something to note. It was just something I didn't really know what it was. It'd been nice to know beforehand. And then the final note, the BOM. So bill of materials is obviously a huge FSAE document. Kyle did a great presentation on how to do it. I wanted to mention it for here because I had some difficulties with it for suspension. I feel like it'd be a good idea just to mention real quick. All suspension components have to be included in the BOM, just like all components on the vehicle. This will directly ensure that all the parts and assemblies you made are designed properly to the rules. So there are specs like all the parts you designed, the stock size have to be 40 thousandths past each edge. You have to go through and make sure all of the holes are developed properly, are mentioned properly. All your fasteners have to be there, all the little nuts, bolts, how you're going to put this on there, the jig has to be included, all of that. So you got to make sure that it needs to be there. Over spring break, it took me Monday through Friday, about 8 hours per day, to go through, confirm everything was designed properly, and confirm that I was able to get into the BOM properly. That's just what it was for me. I was able to get it done, but it took a while, and I want you guys to just be aware of it, that it kind of creeps up on you guys. We were like a couple weeks coming up on spring break, and I was like, hey, we got to start working on BOM, and literally April 2nd, which was the first, I think it was a Monday back after spring break it was due. And so it was kind of like, that was my whole spring break. So just be aware that it's there. And it's a big document. It's a little clunky, but it works, and it might take some getting used to, but you really want to have good design goals in mind to make sure you're going to meet that deadline well. And so that's pretty much it. Yeah, go for it.
Yeah, on the BLM, is there like specifications that they put for the competition? Like how it should look, or is it kind of just...
So it's all done through the FSAE online website, which is pretty convenient. And the short way it works, the way it works is if you have a part that you're going to design, like the Bellcrank, you got to say, this is the material, this is the stock size, this is how it's going to be made, whether it's CNC'd or whatever, this is the volume that's going to be reduced off of the CNC, that's the machining price. Then you got to go and say, this is how it's going to be fastened to the vehicle. We're going to use these bolts, these spacers, these nuts. There's a cost for someone mounting it properly, there's a cost for it being tightened down, that type of thing. Once you get all those done, bam, that's done. And you got to go to the next part. Items like the DVO shocks that are already purchased work a little bit different in that you just send in a form to them. We say this is something we've designed or we've purchased directly that was not in your catalog. If it is in the catalog, then you just pull it straight onto it, pulls the price right in, you're good to go. So these are already in there. Another reason to keep using them. So, any other questions? Yeah, go for it.
Yeah, what would you say, just being a team lead, what would you say was the biggest challenge in the design process from start to finish?
Not knowing where to start. My biggest thing, I came into this, I really only had a decent understanding of mountain bike suspension because I own one, I think it's cool. It's really fun for me. So I came into this knowing how mountain bike shocks work, how an air shock works, how linkages on mountain bikes for the most part, how they work, motion ratios. And I came in, the chassis was designed in SolidWorks. And it was, here are the points where the upright's supposed to be, here are the controlling points, fit a suspension system to this and make it work. That's not how it's supposed to be done. So I made it work. And we're going to get reamed on it for suspension at competition, but it is what it is. So not knowing where to go was a big issue. Hopefully, like Kyle mentioned last week, the groundwork has been laid for you guys. It's going to be way easier for you. I'd say way easier. It'll be a little easier to start for you guys next year with a baseline. We know this worked. We know this didn't work. Let's go from there. So yeah, that was probably my biggest thing.
When are we starting? I'm sorry. When is like the design for the new car?
The new car is pretty much starting
now,
as soon as it can. Yeah, pretty much
it's
now.
starting now.
Yeah.
It is.
Next year's car is going to be an iteration off of this year's car.
Right. We've mentioned that we want to kind of make the chassis about 5 inches longer than the IC car because the current EV one is huge. It's for people that are like taller than Zach, which is ridiculous. So we want to make the IC one just a little bit longer. And I would say take some of the data from IC that we get on how the DVO shocks work, how they react, any of the data we get from EV, take it, make sure it works, understand it, and build from there.
Are we doing 2 cars, EV and IC? Again?
That's the goal, but probably not. Next year, yeah. Next year we're just doing EV. For the next couple of years, we'll be doing EV until the club feels that we're established enough. And if there's a big enough group that wants to do another IC car, then we can do a second car.
We'll call it just EV.
But yeah, EV for now is the best way to go. So, any other questions? Go for it.
So for next year's car, you were mentioning that for the design process, you would basically be starting with the suspension system and then designing the chassis from there.
So yeah, chassis is supposed to be designed last. Chassis is connecting the points. You get suspension developed, you have your tire data kind of to develop your suspension, you get your suspension points out there, you get your lines drawn, you say, great, this is how I want all of it to work. You have your other sub-teams that go in there, have rough ideas where they want to go. We have the driver mount, that's very important, where the driver's going to be sitting, how they're orientated and whatnot, or oriented, and going from there. With that in mind, then you start just connecting the dots. Ideally, the chassis is the last thing designed and the first thing made. And that's what kind of makes it a really difficult balance, is going through and kind of having a hard cut, we have to make the chassis now, and immediately getting it made. So.
Sweet. I have just one more question.
Of course.
I know this is kind of like a hard question to answer, but when do you think, in terms of just like the whole span of designing this car, when do you think the suspension should be completed? Like the design of it?
Week 1 of fall quarter would be ideal.
So working over.
So over summer, the suspension team meeting from wherever, remote using Discord or whatever, to just go through and, okay, this is what I've done this week, this is what I think we should do, I like this idea here, this worked at competition, If we can still do testing of EV and IC over summer, excuse me, that would be awesome. So we can get some more data there. Like, hey, this really worked today, this really didn't work, we should go this route, we shouldn't go this route. Making decisions as a team and going through and developing from there such that week 1 hits at school, you're like, bam, suspension's done. Where are the other sub-teams? When can we get this frame made?
Yeah, really it'll come down to kind of the leadership of like Tim and Aaron, figuring out the overall, like very high level, what do we want out of this car? And then the second that that is determined, suspension.
Yep.
That's it. So you'll work a lot with leaders figuring that out.
And Tim's got some pretty good ideas for the next year, suspension, just some baselines that he wants to work with that I think are going to be really cool. It'd be a great place to start.
Okay. I think I've already told you too, but I'm really proficient in SolidWorks. I've been working, 6 years or so in various companies, but I would love to use that and be like one of the main people to design it, because I'm really efficient and very fast in it. So
that would be super cool between the suspension team, how you guys want to orchestrate that, and Tim and Aaron, and go through and try to get some ideas fleshed out. It'd be really cool if going into summer, right there, finals week, getting everything kind of sorted on the team, so that, okay, you're going to be kind of in charge of this, you'll be kind of in charge of that. Obviously, we're all working together doing the same thing, but we got to be in charge one way or another. Yeah.
Just one comment before we end is it's really, really easy when you're just starting something like this to realize, oh my gosh, there's so many assumptions I need to make. There's so many things I don't know. You guys will have a better idea how much the car's actually going to weigh, but Trevor had it was just like, well, other cars weigh about 500 pounds. Let's do that.
Give this a shot. And again, I went off the DVO shocks just assuming we can hold pretty significant weights with those. I was actually kind of happy to hear that on the IC car we were eating through all of our travel. I was concerned that it would be so stiff in the most open setting at 100 PSI, their minimum, that we get no travel. But we were immediately eating through travel and things, so I'm like, perfect, we can actually tune this properly now. Another reason why I wanted to stick with the air shocks, because they're just fantastic. I think you can really right a lot of wrongs with a good air shock if you know how to use it, and you have a decent system that you know is going to work and not destroy itself. So, but that's a very good point. There's a lot of complexity to this. Again, don't expect to know everything. Just try to pick a couple goals, a couple things, go with them, try to design them, try to make them better, and make your hard cuts so that, okay, at this date, we really can't be doing it anymore, we got to move on.
Don't let having to make all those assumptions discourage you.
Not at all.
It's going to make you feel like you have no clue what's going on, and the truth is you don't.
I have less.
But no one else does either.
Right.
So you know what I mean? Like Trevor says, he has no clue what's going on, and I believe him, right? Like 20-year-old veterans still have they're like, this is kind of how it works,
Right.
But he's the expert here. You know what I mean?
As close as we've got.
So you can't let that discourage you. You just need to take what you've got
and run with it.
Go to Google, go to the resources we have, find new resources, and just figure it out. Don't let it discourage you that you feel like you don't know anything. And then also, while you are making assumptions, when you have a design and when you have hard numbers, right? Like when we know the car's going to be between 400 and 450 pounds. You need to be very careful when you're making your assumptions in your simulations.
Right.
Because one mix-up, even something as simple as like fixing a face instead of actually bolting it with hardware in a SolidWorks sim can give you totally different numbers. Like the difference between a factor of safety of 10 and a factor of safety of half.
Yep.
So, there's a time and a place for like kind of guessing and making an educated guess, and then there's a time when it's like, when you're doing the sim, you need to know. You need to have a really good guess, or you need to guess way over.
Especially on the Bellcrank sim, use that Bellcrank optimization on the SVN. That's a great document to give you a great start on how to do Bellcrank sim. I had no idea how to do it going in, read the document, asked Kyle a couple questions, figured it out.
Well, not only will you have access to like the SVN, but where all of us are graduating, but it's not like we're going to disappear off the face of the planet. Like,
we'll be involved in one or another.
We're all going to be around.
You also have hopefully you'll have two fully functioning cars with those shocks on.
Yeah.
Exactly, which is huge because you get so much data from those.
We've already learned more than we've probably known in the past year about those shocks by doing like one test day with them on a fully functioning car.
Yep.
And it only took us 5 or so minutes to adjust it, to take a car from that pushed like shit and understeered like crazy. It took us like 5 to 10 minutes to adjust air pressures, compression, rebound, fix it.
That's
So like you said, you can fix a lot with those shocks.
Yep.
Right.
And we have that luxury that teams 3, 4, 5 years ago didn't have.
Right.
Because air shocks have come a long way, and that shock's only been on the market maybe 4 years. That particular one, at least.
Any more questions?
Any other questions, guys? All right. wants to push everything back. So you've got the spring system being created in the air and the damper system of the fluid helping to control it. So that's how these work in the simplest way. The reason we wanted to go with these is they have a very simple switch here, which allows a quick adjustment of compression. So if we're too far open in one setting and we throw the car, we can tighten it up immediately and see if that makes a difference. Likewise, if we're really, really stiff, we can open it up a little bit more and see if that makes a difference. They offer rebound adjustments, just as the Jade does. Just if it's, the driver's noticing that the front is kind of really coming back too quick, we can slow it down, or if it's really sluggish, we can speed it back up. We can also change these by just adding or taking away air in both the positive air can chamber and the negative air chamber. The best thing about these is they're completely tunable on the spring curve. First off, it's a progressive spring curve, so it starts out kind of slow, meaning you take up a lot of your shock travel for less force, and then ramps up pretty quick to be really hard to push all the way through its stroke, just because you're compressing air much like you would in a piston cylinder assembly in a motor, like diesels can self-ignite, right? The best part about that is they sell air spacers on these, which you can put into the air can, as many as 6 on the positive side, which make that ramp up much faster because your air has less place to go. So if you have a car that you've got your suspension decently tuned, rebound's good, compression's all right, but you're diving straight through your travel, but everything seems pretty good on the driver's side, slap some air volume spacers inside, then give it a shot. It'll keep the same small bump compliance without eating up all of your travel so quickly. Go ahead, Matt.
Is this kind of like, this is a little bit beyond the scope of the fluid dynamics class that I took, because it goes into like compressibility of fluids, like air or whatever. Could you also take a shock like this, or are there other shocks that use a different gas like nitrogen? Or
nitrogen is very common in these, yes. Fox has been known to use nitrogen in a bunch of theirs. Devio keeps it simple and just uses air and air so that any guy in his garage can do it. That's another thing I should mention here. I didn't mention on the slides, but I will mention here. These have been designed to be extremely tunable, but extremely easy to work with from the consumer side. Your garage mechanic can easily pull all of this open, service it all, change everything he needs to. We can do it on the fly on the track if we need to. I'll be showing you guys how to do it here soon, and we can go from there. Go ahead first.
So that was one of the things that I was wondering about also is, as these shocks are cycling and they're doing their thing, they're dissipating heat, are they going to change their performance characteristics because of the fact that as the gas heats up, it's going to be under more of an initial pressure? Exactly right.
Devio has thought about this, and I've actually talked with John Polino, who helped design this, about it. He was a brilliant designer when it came to this. It's hard to see from here, but there's actually cooling fins on this air tank here, or the negative air chamber. The reason they have fins on those is as this is getting compressed throughout an entire run, on a mountain bike, for us on the track, air is heating up because we're compressing all the time. It heats up, it has to. So what's the best way to dissipate that? If your cooling fins on here, they've actually found that the cooling fins have made significant differences in the performance of these. You're getting you're keeping your compression relatively good, and you're keeping your rebound from getting too far out of control. As this heats, your compression gets stiffer and your rebound gets faster, which are the two things you don't want.
I will attest to that. We tested maybe a couple Saturdays ago on the IC car, and I mean, you can ask Eric, we were tuning suspension, we do 4 or 5 laps. If you touch those, they're hot. Like,
yes,
they are
and this is
warm.
with the fins. Yeah. I did a run up at Snow Summit on my mountain bike with one that didn't have this air canister. I almost burned my leg after one 8-minute run. They get hot.
So that was another thing I was curious about. I'm guessing there would probably be a benefit to setting your suspension where you see your suspension characteristics after everything had warmed up and gotten in kind of a steady state.
Yeah, so you can
setting everything cold.
You can go a couple ways. You can go a couple ways with that. So competition, there's a couple of the really fast events, just like your acceleration or braking test. Then there's endurance. So with the acceleration braking, set this up to be a little stiffer. You're not going to be blowing through your travel. You might on your front, so you'd be a little stiffer on the front because of the braking. Acceleration probably all right. For endurance, these are going to heat up. So that might be something we want to keep in mind and run them a hair lower than we normally would. And this could be some testing we might be able to do on Saturday. Do the first couple runs with where the suspension is. As it heats up, see how it can change, and we can start testing from there. The reason I'm so glad we're going to keep using these, at least for this next year, is we're going to have all of the IC car data that can then move into the EV car data. And that's going to be huge to have some basis to start with.
As for some of the adjustments you said that you can make, are any of those able to be done electronically? Like during...
Like on a dyno or like...
Like while you're driving, can you adjust your suspension?
Not while you're driving. The vehicle would have to be stationary. If you wanted to, you can do some of the like inserting the air volume chamber or air volume spacers into the air canister while it's on the vehicle. You just take the air pressure out, you slide a O-ring off of this, and this pops straight off. You slap the O-ring in, or the air volume spacer, pop this back on, throw your damper back on, air it back up to pressure, and you're good to go. Yeah.
I wonder if what Trevor's getting at is kind of like an active suspension. So as like progresses, as you get hotter, as you drive the car more and more into endurance, you have it on the fly. Do you know of any suspension like that?
So no active in mountain biking. The closest we can get into active would be the compression adjustment. And so if we start, say, super stiff on endurance and it's starting to heat up and getting stiffer and stiffer, go to the middle setting. That's immediately going to open more, open the ports more for the fluid to be going through, and going to allow this to compress a little bit easier. Then if it's still getting hot and hot, we go to the complete open setting. So there are small things we can do like that, but nothing that's going to, got an onboard system that can account for how much temperature we're getting and going from there. Yeah, go ahead.
Would there be any sort of benefit to implementing some sort of cooling system that goes over the suspension, or is it okay to just understand that it hits a certain steady state and
goes
you
from
just
there?
do your testing from there?
Yeah, that would probably be better because again, these are designed to be air cooled, and the way these are designed to sit in mountain bikes is they sit within the frame, like in the plane of the bike. As the bike is moving forward, the only air it's getting is the air coming around the frame. Ours are going to be perpendicular to the direction of motion, so they're going to be getting a lot more airflow over them, which will help cooling. Granted, they still got warm, but it's better than what it's supposed to be on a mountain bike, which is good to know. And after I did talk, like I said, to John Polino, he mentioned that for our purposes, he says that these probably won't be hammered nearly as hard as they were on a mountain bike, which is good to know.
What's the advantage of using air in contrast to fluid?
Air is compressible, fluid's not, mainly. That's why you have your fluid between the two different air diaphragms. So your air compresses, moves fluid, and then compresses the air here, which wants to push it back through. Okay? So that's why we're going with the air shocks. I'm partial to them just because I own one for my bike, but they're really cool. They allow a lot of, like I mentioned, tuning ability, which for a suspension system like the one we have on the EV car, it's definitely not the best. It's going to be a saving grace for a lot of cases. So going into that now, the suspension design for the current EV car. I designed this with the wrong process. I did what's referred to as an iterative process, meaning I had points. I kind of had some idea of where it was going to go, what it was going to kind of look like, so I just took some shots at it and went for it. I went through about 40 iterations of Bellcranks on the front, about 20 in the rear from when I finally got an idea of how to do it. And that's how I just connected points and made it work. I was really only given with the shocks have to sit on top of the frame, don't worry about the body, that'll get cut around them, won't be an issue, and just make it work like it's supposed to. I'm like, okay, great. I wanted system that works, clearance for the motors and the upright assembly, and then I use static camber, meaning we have our camber fixed at whatever angle it's going to be. That means the wheel throughout the entire travel is going to be vertically up and down. There's going to be no side-to-side motion, no changing of camber. I wanted to use that because it was a very simple datum to go by. Some of the literature I read said that's a really good place to start if you don't have anything else. So I'm like, perfect, that's exactly what I'll go with. I think it's going to work out decently in that sense. Ben?
So if you wanted to account for camber change, how would you change the suspension to account for that?
So if you wanted, you would want to make it, if I recall correctly, such that it angles itself out so that the contact patch, as it's moving through, would be rotated slightly. Does that make sense?
Yeah.
A system like that should be changing camber. I'd have to do some background to double check that, but that should be the way to do it. Now, system has a few drawbacks. The push rods, relative to some of the other vehicles like the IC car, are super long. Why is that bad? Well, because the longer you have on a piece, that's going to be a tension compression rod. If there's any out-of-plane forces, you have a much longer movement arm that's going to cause compliance and issues. Especially considering on the push rods, we've got the threaded rod ends, which easily fail in bending. Those are not loaded like in that way. They're only good for tension compression. And I have no anti-roll bar, which I'll get into that again here in a minute. That would definitely be helpful considering the amount of unsprung weight we have on this vehicle. So here it is. This is what it looks like in SolidWorks for the rear. A little easier to show the rear than the front. Again, double A-arm system, two-piece solid Bellcrank. And so what I mean by two-piece is the Bellcrank is going to be made out of two identical pieces that are just kind of sandwiched together and rocked together with the spacers and the bushings. It would be better if we could do a one-piece bell crank, because one-piece bell cranks, although a little heavier, tend to be far stronger, especially in bending, which would take away a lot of the compliance. I know Cam was super into that this year. Sadly, we weren't able to make it work. It'd be something I would love the next year, guys, to keep an eye on. It'd be awesome to do. I've got a two-piece shock mounting with additional brackets, so that's that big piece right up here at the top. That's just 2 plates, identical shock mounting, and then I've got some additional plates in the middle, kind of on the bottom, just to add a little bit of rigidity against bending, because that's going to be the point at which there'll be the biggest moments, because it's being transferred through the whole system. And tie rods and uprights I don't have here shown just because it's convenient. One thing I want to point out is the push rod actually mounts to the control arm, so that's where the 2 control arms meet, which is a kind of an unusual design. Normally the push rod is going to mount to the upright, but because we have so much going on with the motors this year, it was kind of decided that for clearance issues, to make it a little bit tidier on the upright side, we'll put them between the control arms, weld them together, and we'll be good to go. So that's kind of why we did that, and one of the reasons behind the current suspension. So some simulation that goes into this. This here was a one-piece bell crank that was done from the Bellcrank optimization book, or I should say PDF. That was a master thesis for an FSAE team in UCSD in 06. Yeah, it does a great job describing how to run simulation in SolidWorks for bell cranks. This is how I did it off of mine. They basically were able to generate forces based off, they had coil springs at the time. I went with the same numbers. We now have the DVO shock data directly from DVO, so we can go straight to that to begin with our numbers, go right to the maximum for whatever our settings are, and we're set there. And this one here, the whole thesis was using topographical something or other, I forget the exact term, to make it optimized for the best amount of performance versus weight, which is an interesting thing to do for suspension. But it worked out really well for them. I was super impressed to read. They had a whole system set up to test this, and it was way more impressive than I thought it was going to be. So this is the one that I designed here. Far simpler. The reason it's completely solid is because the way I have the suspension designed. So in fact, I should go back and show that so that it's a little bit more clear. Here, I want to point out that the push rod mounts to the middle, whereas the frame mount is actually one end here. It's not supposed to be done that way normally. You usually want your frame mount to be right in the middle of the bell crank. And the reason we want that is if my pivot point is right in the middle of my bell crank, my force goes straight over it. If I have the pivot point off on the middle, on a side here, I've got significant bending moments that could be generated about that. Sadly, in order to make this design work, I just had to bite the bullet and go with that. And that's why I'm going with solid bell cranks, so they'd be a little stiffer in your bending. There wouldn't be nearly as much compliance in the part itself. Even with that, I'm still running about a 2.5 factor of safety on it after double checking the sim, which is convenient. And again, this was before I had the Topaz force curves. So at 150 PSI, 6 spacers in that, you're generating 900 pounds of force. I assumed we'd have 1,000 at most. And again, so we're going one piece versus the 2-piece. 2-piece would be awesome because it's just far stronger, does not have nearly as many issues in the bending. Would be awesome to do.
One
Does that
piece,
make sense?
right? One piece is stronger.
Yeah, one piece, excuse me. Yeah, one piece is what I meant. Yes, one piece is far stronger than 2. Go ahead.
Can I ask what the arrows represent?
So, yes, so that's actually a good question. So the way this is set up, and this is all based on that document which is on the SVN, this here was my fixed pivot point. Again, it's not supposed to be here. This is just how I had to do it for this design. This here is the load coming in from the push rod, and you have to break this up, and the document goes into good detail about how to do this, into component vectors to make this easiest. So I've got one component vector here, one component vector here, both of certain forces. This is off of the shock trying to go against that. This is, again, component vector, component vector. These angles were determined by taking my suspension and putting it at its maximum, which would be 100% compression. I have one angle of the push rod coming in and one angle of the shock coming in. So I just took those angles, made them off of the, I think I did as close as I could to perpendicular. I'd have to double check exactly how I did it. But again, that document does a fantastic job of describing how to do it. After that, I was just running a few sims. It wasn't too bad. But this is completely fixed. These are bearing rods. That was the way I did it. Does that make sense? Go ahead.
Yeah, also, just real fast, you said that you have two-piece bell cranks. What trouble did you have, like, in order to create just like a one-piece? Like,
so one piece, it's first off machining, because you have to take a block that's the size of one bell crank, machine all of it out, and if you're going to do weight savings, you got to do optimization in 3D as opposed to just a simple 2D optimization like this.
So it's
These
just
are gonna
difficult
be,
to machine.
yeah, it was manufacturability and simplicity. These were going to be way simpler to make. This is a G code that Aaron could probably do now on the CNC, just rip through it, we're done. As opposed to having Kyle go through and do a complex G code and taking it from there, which could be a significant amount of time and cost.
Yeah.
That for this, just to get it working, may not be unnecessary. We'll have to see how they do, which I'm interested to see how they do. So in general, why do we want to simulate the Bellcrank as opposed to any other systems on here? Well, the Bellcrank is what's moving and it's what's going to experience the most forces, especially at maximum compression. So it's the most complex part that we currently are designing just because that's what's moving, that's what's seeing forces, that's what's got to transmit the force from the push rod to the shock and vice versa, shock back to the push rod. So it would be awesome if you could do testing of the Bellcranks, optimization, allow for weight reduction, especially if you're doing the one-piece Bellcrank. That's something that we really don't have. But again, that Bellcrank optimization, something like that, would be super killer for this. Because teams that are saving weight on Bellcranks are the top teams. Not many can do that, just because it's a very sketchy component to start trying to simulate and save weight for that type of, oh, we saved about, I don't know, 1/4 pound across all 4 corners. That can be significant for these teams. That can be the difference between 500 pounds and $4.99, like the IC card. So it really depends. Now I want to make sure you guys are aware, Kyle brought this up last week, but there are different simulation softwares that are out there. We've got Optima K directly for suspension. Optima T is tire data. Vehicle and track simulation is Optima V. That's where you can go in with the vehicle in as the model and run it through the entire track that you can design and see how it does in the worst corners, the best corners, how it accelerates, how it brakes. And then these are all owned by the company Optima G. Kyle has mentioned before, we can purchase these if there is interest. The last suspension guy, Rudy, was getting into, I want to say Optima T, but there were some issues with it, wasn't able to follow through. So, some improvements on the current design that I'd like to go through. Anti-roll bar, which I brought up a few times now. So the anti-roll bar, the reason these are nice is they couple the 2 parts of the suspension between the left and the right side. So for the front, you have one anti-roll bar, in the rear you would have an additional anti-roll bar. And it does exactly what it sounds like. If you don't have one and you dive into a corner, you're going to take up all of your outside travel and leave most of your inside travel, as it's probably going to extend. So that means your chassis is going to be then tilted. If you're going to use a anti-roll bar, what it does is by coupling them, it's going to dive the inside one, but it's also going to want to pull so much on the outside one that it wants to level the vehicle as best as it can just by using twisting forces, just usually torsion on these. And so it levels the vehicle out in corners, which allows there to be a better distribution between all of the tires and allows you to have better track performance. In ours, I think this is such a good idea because we've got so much unsprung weight. I feel like the vehicle's really going to have issues diving. I think an anti-roll bar would have been really, really nice to have on this. Go for it.
Were there any specific reasons why we didn't have it in this car?
Probably because I didn't really know it enough in time. I didn't do enough research into what an anti-roll bar was, how to make one, how to design one, how to use it until it was really too late for me.
Yeah.
Likewise, the judges are really, really strict on stuff like that. That's kind of above and beyond.
Right.
Like, they would rather see no aero at all than aero that wasn't planned out well, an aero that wasn't simulated well. And so, if we weren't positive that we were going to need an anti-roll bar, and we didn't really understand it at the time.
Right.
And so, like
So
Trevor said, it
suspension-
was just better to not do it. And now, if through testing we decide we need to, now he understands it a little bit better. Now we know what to do.
The new guys know about it before even designing one in the first place. I think it might be a good idea. Could be a great solution to go through and design one without, and then design that same suspension, just tacking one on and seeing what effects that might have. There are some pretty significant physics behind it. It is still a complex piece, but it is the above and beyond piece for suspension. That is correct. It's a great way to say it.
It's also kind of a bitch to package.
Yes, it is.
Where you
Especially
really
for
want an anti-roll bar is typically in the front, and we already have so much shit going on in the front, like a pedal rack, and adding an anti-roll bar is like adding a whole nother steering rack to the front end.
Right.
So it's kind of a bitch.
Go ahead.
Well, and I would imagine one of the other problems with putting an anti-roll bar in this is finding one that would be sized for the vehicle.
You
because I
probably
would
have to make
imagine
your
it's not
own.
something we can make.
Yeah, we would probably have to try to machine our own, but it would definitely be interesting. I haven't looked into it too much again, just because I really don't know enough about them. But it is something that a lot of Formula teams run. I'm not sure exactly how many FSAE teams are running them, but it'd be interesting to know. I'm sure Wisconsin's, of course, running one for them.
Good amount of teams.
They're not
Are they?
uncommon. They're not.
They're not uncommon.
Okay.
Every team has to just about make their own though.
So a lot of teams that run anti-squat too.
Yeah, that's true too. So yeah, that's the anti-roll bar. That would be something I think would be awesome to think about for the next one. Another thing that was brought up, camber, I've discussed this a few times. Camber is just the angle of the tires relative to the vertical of the vehicle. Like I said, for mine, I developed it with static camber, and the reason for having just a straight static camber, keeping exactly what it is it's simple, it works, and it's pretty optimum for what we're going to be putting the vehicle through. But there are a couple situations where dynamic camber can be more useful. If you have a dynamic camber and you're throwing the vehicle into a really hard corner, dynamic camber, by angling the tire, that outside tire, one way or another, you can generate additional loads that are going to want to turn the vehicle more, which could add to oversteer, which on these you always want to have, you really want to have a neutral car, but if you could, you want a little more oversteer than understeer, especially with how Tim and Ryan were finding out with the IC car.
Little side note on
Go ahead.
that. Mercedes had actually made, I forget what model it was, but have you seen it? It had dynamic camber, so the
I
wheels
don't know if I've
actually-
seen that one.
Yeah, in the corner, the wheels would
Yeah.
camber themselves. It never hit production, but it was just a wild concept.
Yeah.
For
So,
us,
go ahead.
typically not dynamic camber, like not dynamic, it's just camber gain. So as you compress suspension, the camber ends up technically decreasing as the suspension is compressed. So it doesn't change, like, it's not a computer controlled system, it's something that's implemented
Mechanically, yeah.
that just happens.
That is a good way to say it. The texts I've read have said dynamic, assuming I think they mean the camber gain of the suspension. For those that don't know, an easy way to think about camber is on a bicycle. If you're going straight and you lean to the right, you tend to turn to the right. So if you lean the wheels one way or another, you're going to generate turning forces one way or another. Go ahead, Matt, you got a question?
Yeah, so you said like, you were talking about camber gain. Does that mean that the tire flattens out when you're going into a turn? Or
Depends if you're running positive or negative camber. So if you're running like a negative camber gain and you're starting at like say 6 degrees, you're going to lower that as it runs through its travel. If you're starting with say 6 degrees and you're doing positive camber, it's going to get more camber. It's going to go further through the travel and further into the tires one way or the other. Positive, I think, is whatever it says here. Positive is angled such that so the bottom is inside, whereas the negative, the bottom is outside.
So do you kind of want to have, like, let's say you're looking at the outside tire, like if you're turning to the right, the left front tire is going to be having a lot of traction or force put onto it. Would you want it to kind of have some sort of a, like almost a flat angle so that you have the most amount of
Traction.
tire patch hitting the road? Or
Yeah, and again, remember that when you're, the whole point of turning is when you're throwing it onto that outside tire, you're getting a distortion at the tire. I should have thrown that diagram in here, actually, it was really good. You have the whole, like 90% of tires vertical, that last 10% on the road is distorted, and that wants to create turning forces, right? If you have camber that changes that amount versus inside to outside, if you change lateral loads there based on how much force you're diving in on that one tire for traction, that can turn the vehicle more or less for you. And a big thing I know was, again, for Tim and Ryan, was really struggling with understeer on the IC car. So that could be something to think about.
So the way that dynamic camber would be implemented would be to change the initial camber of the wheels, like to start them out as tilted and then to mount the suspension such that as they turn, that would
As it goes through its travel, it would be angling more or less.
Okay.
That's what we're going. So static camber, we fix it at some amount and it stays that the whole way through.
Yeah.
Dynamic camber is that as it goes, it changes one way or another. Depending on what you want to do is what we should look at in physics.
So another thing that I don't think Trevor really mentioned is that the tires aren't like non-deformable. So if you don't have enough camber, they can actually roll underneath so that you're not running on the traction side of the tire, you're running on the wall of the tire.
Right, which
And
can
so
cause issues.
6 degrees is like a lot of negative camber.
Yeah.
You would probably never see that on any
I was
car.
reading through some of the literature and that is a lot.
It's a lot of negative
Okay.
camber.
Well, actually, on the subject of negative camber, you brought up the Milliken and Milliken suspension book. And I remember running across a car that Milliken built. It was called the Camber car, where he, and you may have run across this too, where he experimentally tested ridiculous degrees of positive and negative camber, like up to 50 degrees
My goodness.
negative.
Just to see what would happen.
Yeah, and the car still survives. Look at it, it's called the Milliken MX-1.
Oh,
And it's
look
just
at that.
this
I don't
absolute
recall that one,
freak
so
of a
yeah.
car.
Yeah. But that's a great way to do it, to just go through the extremes and to see how it really is going to work through the whole system. And again, remember, there are a lot of variables going on in here. If we say we want to do dynamic camber like 2 degrees per inch or whatever we're going to do, having dynamic camber, so camber gain change throughout, changes a lot of the other characteristics of the suspension and the tires. And that's why it's another one of those things that might be you want to keep an eye on if it's something we want to do or something we don't want to do. Everything we're going to tweak on suspension is going to affect a whole host of variables in the way the car handles in general. There's really not one thing we can change simply, except maybe on the shocks we can change compression, change air pressure, small things like that. Hold all things constant, and we can kind of tune that way. But if we're going as far as like dynamic camber and the software and whatnot, that's going to be difficult. And I think that's where some of the Optima K software will be really helpful, the suspension software. Go ahead.
How would you suggest creating an adjustable camber system in terms of like setting it at, say, -3 degrees static camber, then changing it when the vehicle is stationary to like -4 for testing, and then we can find an optimal degree that way? How would you go about designing something like that?
Did you want to answer that, Zach?
Yeah, that's kind of how the current upright was designed. You can pretty much shim the top of the upright forward or backwards, depending on how much camber you want. It ends up being a bitch to take off and put back on, but I mean, it's able to be done if you want to adjust it on the fly.
Yeah, so that's on the upright side.
Shims are typically a really good way to go because it's consistent. You put a shim in there, the width of that shim doesn't change, so it's consistent, it's repeatable. Some cars use turnbuckles too. You just adjust kind of a turnbuckle on there, and that changes the length of the upper tie rod of the control arm, and that changes your camber too.
Yes.
Is there a way that you can use suspension to sort of manipulate the weight of the car such that it's evenly distributed on each side of the wheel, such that camber isn't as much of a problem?
So you always want to try to balance the car as best as you can. On the IC car, we had an interesting thing where it was like the front left, was it the front left, was like significantly lighter, I want to say, than the other 3 corners. Ideally, you want to have equal weights at all corners, because that's a great baseline to start with, where if you change pressure in front versus rear, you can easily see differences. When you have a difference of 20 pounds, one corner versus another, there's a lot different. The inertia there is different, and so changing it, tuning it's a lot harder to follow. So for your question again, it was?
I more meant that for each wheel, right? Normally the weight's being placed on the inside edge of the wheel, so when you're turning, that kind of thing, then you get that camber change.
Right, to go to the full contact patch.
Yeah. So is there a way that you can distribute the weight on the inside edge and the outside edge of the wheel such that you don't get as much camber?
I think that's more about where your upright is mounted inside your tire. Right, so like if you're actually connecting, like, you know, if you've got the tire and you're connecting to the upright in the center of the tire, you're going to be pretty even. But if you're way on the inside of the tire, your load isn't even. Does that make sense? So you're applying some moment already to the tire just by how it's mounted. So that's not necessarily a camber thing. Like if you do tilt the tires like 30 degrees negative camber, yes, you're riding on that inside edge, but that's not the point of it.
Instead of like
The point of the weight distribution across the tire will kind of figure itself out when you're driving. The camber is more to make sure that you get that full contact patch on the road in the hard corners.
Under whatever conditions you want to design it.
Right? So like, if you're a drag car, you want like no camber, right? Because you're going to go in a straight line. Whereas if you're like a really intense autocross car, which is what we have, you want a lot more camber because you're turning really hard, tight, fast turns all the time. And so the tires want to roll under on themselves because you're applying so much tangential force, like sideways on the tire.
Right.
So it wants to roll. So you need a lot of negative camber so that when it rolls like that, you actually have the contact patch. Like that roll is putting the contact patch on the ground.
We care less about the contact patch when we're going straight than we do when we're corner.
Exactly. Exactly.
It's kind of a trade-off.
Yep. Any other questions on camber? Does that kind of make sense? Additional improvements? Yeah.
Well, not really on camber. Can you go over just real quick what's oversteer and understeer?
Yes, so in fact, I don't know if I had a slide on that, but I should have. I may have glanced through without paying attention. So oversteer and understeer refers to your steering, obviously. If you have neutral steering, you go into a corner, every degree you apply in the steering wheel will equal the same amount across the tires. Now understeer, the way the suspension design is you go into a corner, what will happen is you need to start applying more and more and more steering so that you keep getting more and more turning. Whereas oversteer goes the opposite way. Now, a lot of the commuter cars are designed to have understeer because they're very easy to control. You need to get further into a corner, you can just grab more wheel. Oversteer, it's designed in such a way that if you go into a corner and you need, it'll begin, the way the suspension is designed, it'll begin to push the tires more and more with less input, so much so that if you need to, you actually back off of your steering to equalize it. That's where your oversteer is. Your competition cars are designed that way because a skilled driver is going to be able to get himself into the corner and then begin backing off sooner and sooner so that as he comes out of the corner, he's already straight again. Whereas understeer goes so much further to bring it back. And again, that was the problem with Tim. You want to say something on that?
Yeah, so oversteer is drifting.
Yes,
So,
that's a great way to
so
say it.
it's basically controlled, or drifting is controlled oversteer, right? The tail end of the car is sliding out sideways, that's oversteer. The tail end is sliding out and you're having to compensate for it. Understeer is you go into a corner and you turn, but instead of your back wheels sliding,
Your front
wheels push, and they don't have enough traction to turn you, so then you end up like you keep going straight. That's understeer.
Yeah,
Simply.
another good way to say it. Go ahead.
So from what I understand, understeer and oversteer can be corrected through torque vectoring, right?
Mhm.
But as for, how do you account for them so that the suspension fixes them to some extent before the torque vectoring comes into play?
So on oversteer and understeer, I'd have to look into it a little bit more, but again, it's going to be, if I recall correctly, based on the tire loads. So everything comes back to tire loads on suspension. You're diving hard into a corner and you've got a lot of weight on the outside, and you have, say, an oversteering car, your loads are going to want to push your tires further and further. So say you've got your dynamic camber, you're getting your larger tire patch, so you're able to run higher slip angles, which allows the tire or the vehicle to move further in the direction of the tires.
Yeah.
Then you can be able to begin pulling off of your steering. If you're running understeer, your slip angles aren't going to be quite as high, and so you can't, your vehicle's not going to want to turn as well. So to get further turning, you've got to keep adding into that. So that's kind of the mechanical side of it. Yes, you were correct in that your torque vectoring can spin one versus the other to go one way or the other, depending on how you want to do it.
Yeah.
That's a whole complex set that maybe John can get into next week, but I'm not going to go there.
A lot of it comes down to shock tuning too.
Yes.
We noticed last weekend, you'll notice depending on how much grip the back is getting versus the front, if your back shocks are set up really, really soft, the suspension's going to move around a lot more and you're going to get a lot more grip in the back, which is going to push the front. And it works exactly the opposite. If your back's too stiff and your front's really soft, your front's going to get all the grip and it's going to oversteer like crazy.
I see.
Right.
So that difference in weight distribution is what determines
Right.
whether or not your car is oversteering or an understeering car.
Right.
Okay.
And in general, it's really a good idea to go for neutral steering. Because by going to neutral steering, that's one less variable you have to worry about in tuning. So you can go straight for, hey, let's see if we can get a little bit extra oversteer out of this. So let's soften the front, stiffen the rear. How does the driver like it? Excuse me, it's understeer.
Oversteer.
Oh, was it oversteer? Okay. So then if we stiffen the front and soften the rear, there's our understeer now. And so we can go that way. So neutral is always the best place to go. But if you're going one way or another, shock tuning can take it into effect. So that's oversteer and understeer. Does that make sense? Cool. So a quick note on aero. Again, this isn't something that we might be getting into for a while, but it's interesting to note. The main goal of aero is just to use airflow to get additional downforce. Why would we want that? More tire loads. More tire forces, we need better cornering, better traction, and so on. Problem out of this is it adds a significant amount of complexity to the system. Kyle mentioned on this last week that everything is now in terms of a velocity. It's no longer a constant. So all of your suspension has to be effectively redesigned for an aero body and dependent upon all of the aero forces that are going to be generated, which is obviously a much more complex thing to do. And again, that's one of those things, the best teams run aero, but that's because they've been established for so long. They know how everything's going to work. They know what to expect. They know how to go through it. They can begin, I shouldn't say they know how to go through it, but they can begin to work through it. So again, suspension's got to adjust for it. Another difficulty of this is it can be difficult to model aerodynamics through software, so you've got to have physical testing, which means your team's got to be super on it when it comes to deadlines, getting the vehicle built, and getting vehicle testing done. And the problem is, if it's not working well for aero, then you've got problems you got to make. Your problems you got to fix. You've got to, either take off the aero body, adjust the aero, figure out a way to adjust the suspension as best you can. There's a lot more going on there that you have to get done, otherwise the judges are going to tear into you. They'll probably tear into you anyway, but you really got to go through it. Go ahead.
A semi-unrelated question, but if we're early on in the design stage for a car suspension, how do you estimate what values you're going to have for later on once you've developed the suspension?
So it really depends on what you're doing. Having a baseline to start with is huge. If you have nothing to work with, a blank slate, it's extremely difficult to make assumptions and hope it works. The nice thing about us already having, this would be the first EV car done, the next team can have baseline numbers that we know this worked well, this didn't. Let's fix what didn't work well, let's hold constant what did work well, and things like that. When you don't have anything, you're really just trying to, shot in the dark and go for it. College
Especially
that
things
last
like
week.
weight, like getting
Oh,
the
yeah.
first weight for this EV car is a huge thing for
Yeah.
suspension, because you're just giving the blank slate and saying, it's probably going to be heavier than the last car, but anyway.
Yeah, it could be
Who
600
knows how
pounds.
heavy the batteries are going to be.
Could be 650, could be 550. Yeah, that 50 pounds can make a big difference across all four corners. Could be 500 pounds for all we know. I don't know. Could be. So yeah, that's something to keep in mind if you have a team interested in doing aero. They've got to work closely with suspension to go through that. So I want to do just a quick understanding of how suspension should be designed for the most part. Obviously, this isn't 100% the best way to do it, but this is the best I can understand. Go ahead, Matt.
Yeah, just real quick on the last slide. You don't have to go back, but
Okay.
do you guys have access to ANSYS?
Yes, we do.
Oh, okay.
Yeah, we do have ANSYS. In fact, if I recall correctly, we just got a FSAE ANSYS package like 2 weeks ago, didn't we?
We got sponsored. So usually the
Yeah, we got
ANSYS we
sponsored.
have been using through the school, but we've got the full license fee now that ANSYS sponsored with us. So
Yeah.
a little bit interesting setup, but definitely, yeah, I know what
I was curious about that because I'm doing research under Professor Sundar, and we have to use ANSYS, and so I'm in the process
There
of
you go.
learning it right now. So
Yep.
it might be something that I can apply.
There you
to
go, yeah.
Aerodynamics if we ever want to go there.
That's something to keep in mind. That's awesome. So yeah, we do have access to it. So anyway, how suspension should be designed from the most basic idea. Tire data is the start, obviously, because we have to control our tires. So we got to use specifications, tire size, track width, cornering radii, assumptions of what works and what doesn't from last year. So we really like the tires, we use them. We really like the shocks, we use them. Static worked out really well. We want to keep static camber, we'll go to static. Or it didn't work out well, we think more or less would be better, or camber gain would be better. Things like that can give us some baselines to start with. Then you want to just find suspension points based on the design goals, your tire data assumptions, and whatnot. And they need to be quantified. So you can't just say dynamic camber is what we want, because the judges will rip into you. You got to say we want a dynamic camber of 2 degrees per inch. Why did we want that much? Because in testing, we felt that at 6 degrees it was pretty good, but we went up to -10 across the entire hardest corner, and it was gripping way better. We had far better oversteer. Our driver really liked it. Our lap times improved. Things like that that you can actually justify to the judges. And then again, so the points here include your upright, your control arm points, push rod, tie rod, your bell crank, and your shock points. So what would this look like? In general, this would look like a system here, just drawn in SolidWorks as a sketch on a plane. This is the center of, this plane is right in the center of the wheels. So you go through, you've got your basic wheel dimensions, you've got your frame mounting for your control arms. Here are my push rod mounting points for the push rod to control arm mounting up here, and then going all the way up to bell crank and shock mounting. You can start with the points there. Once we have the points figured out, you can then go through just drawing the lines between them. And it's a lot easier to understand once you have the lines there because you can visualize everything a lot better. You do this for the front and the rear, then you can start moving on. On the suspension side, you're pretty much ready to develop chassis. That's after all of the physics of this has been developed. That, is it the SES sheet? It's just the design sheet? I forget the name of it. Is that
Structural
spread-
equivalent G sheet.
Yeah, the SES, structural equivalent sheet. That has a lot of different suspension parameters that are claimed that we need to be designing for. For this year, when we go to competition with the EV car, whoever's going to be going for suspension, I may not be going. If I do, great. Cam might have to be in charge of this. We'll pretty much have to just tell them that, hey, we really didn't know where to go, what we had to start with, so we just picked numbers from the IC car and went with it. And that's what it is. Next year we'll be much better off because we can have data to pull from, so it'll work, hopefully. So you want to have those numbers in mind, and that's how you can begin, that's how you kind of develop your suspension points. You can pick your suspension points from there. Once when all that's been done, you're pretty much ready on the suspension side to develop the chassis and begin modeling the independent bodies of it. So your control arms, your push rods, what your bell crank is going to look like. If you're doing a one piece, you know what the 3 points are, so then you can go through and start figuring out the best way to get a machine down for weight savings and still hold whatever factor safety and deflection tolerances you need it to, and going from there. So yeah, kind of makes sense there.